Okay, so Edoardo, let me introduce myself. So my name is Christine Content from Chemical Engineering Laboratory, just a neighboring laboratory, you know. Well, just I would like to invite you to make a presentation, but before I would like to introduce the members of this committee. So I begin first by the two reviewers. So the first one, Professor Palmero Paola from Politecnico di Turin, Professor Janice Locke from Riga Technical University, and then the other item, so Maria Canillas Suqueres, assistant professor from Madrid Universitat Politécnica, and Nicolas Dorblin, who is senior researcher from the RMS Foundation in Switzerland, and then the local one. So, David, and Fabien, and of course, supervisor. So, now it's your turn.
Thank you very much, President, for the kind introduction. So, today I will present you the most relevant result of my thesis work, that is multifunctional biomaterials based on biomimetic apatite for thread particles toward the smart antibacterial and or osteogenic on substitutes. This thesis work has been made here at the CIANFLONE of Toulouse under the supervision of Christophe Bouillet, Fabien Bouillet, and David Bressin. And as you can see in the title, the core subject of our work is the realization of antibacterial concepts. Why do we need to obtain this kind of materials? Because right now we are facing as a whole the problem that is the problem of the antimicrobial resistance. Everyone knows that in 1929, Fleming discovered penicillin, and that discovery just changing the nature of the human life, because we started to be extremely stronger against the bacterial infections. What not everyone knows is that already in 1940, Abraham and Shane, who won the Nobel Prize along with Fleming, for the discovery of penicillin, found that the Escherichia coli was developing an enzyme resistance to an enzyme that was able to destroy penicillin. So already in 1940, we started to assist to phenomena of antibiotic resistance. This resistance then we discovered that was possible through many other methods than the enzymatic one, but especially that phenomena from the very beginning was pushing us toward a need of monitoring of the antibiotic use, of a continuous research toward novel antibiotics and novel antimicrobial materials, and of course a careful utilization and a careful prescription of them. On the other hand, what happened? It happened that we started to use the antibiotics in the intensive farming and the intensive aquaculture to overproduce animal products. We overprescribed and we wrongly assumed the antibiotics as a human species. And then we fell victim of what the Greeks named hubris, that is the tendency of the human to just feel too strong, too big to fall. And we basically stopped to look for novel antibiotics after in the 60s and in the 70s, we started to have plenty of them. That opened the doors to what ex post we can define as the discovery goal. Now, even though we know that we should control the use of these antibiotics, a recent report published in 2023 on Nature just tells us that from here to 2030, the use of antibiotics in the intensive farming will even increase from the point of at which we are right now. But to put that in number, what does it mean to have this kind of phenomenon? Only in the European Economic Area in 2019, because of the antimicrobial resistance, we had a new infection every 45 seconds, more than 33,000 deaths, and more than €1 billion in healthcare-related costs. And the ECDC and the World Health Organization also foresee that from here to 2050, we will have countless infections only due to the antimicrobial resistance, more death and cancers, and an economical impact just on the healthcare system comparable to the 2008 crisis. To understand better in number the impact of this phenomenon, we know that between 7 and 10 persons that are hospitalized can get a nosocomial infection. Among them, and these are data only related to the European Union, where we suppose that the standards of hygiene and protection are even higher than many parts in the world. I was saying, just in the European Union, it was noticed that the percentage of people in intensive care units that had an infection in 2000 the percentage of people infected in the intensive care unit that had an antimicrobial resistant infection in 2017 was of 54%. That means that 30% of them died in the hospital. And the worst part is that 66% of them got infected in the hospital. Among the many infections that they can get in the hospitals, the most dangerous and likely not the most frequent are the surgical set infections. These infections account for a small percentage of the total number, but can, depending on the site where they happen, increase the death risk from 2 to 11 times. And worst of all, they are accountable to the death of 4 patients out of 5 that get that. Of course, as you can see in the picture, the surgical site infections can happen in many different sites. The bigger is the surgical site, the worse is the risk. And of course, in the orthopedic interventions that frequently involve very big surgical sites, the risk is even higher. For this reason, the finance and the research in many projects was improved. And one of those projects is the AIM, Antimicrobial Integrated Methodologies for Orthopedic Application, an ITN Marie Curie network that involves 10 academic partners and 7 non-academic partners, and that involves also my thesis, in which I am, and in this project I am the early stage researcher number 4. The main part of my research activities were held at the CIANFLONE of Toulouse, between the EMP and CSET where we are right now, and the Faculté de Santé at the Université de Sabatier. Other experimental activities were held at the Centre de Microcaractérisation de Mont-Cassin, at the Fédération Fermat, at the INAM in Forcaim, and at the Universidad de Loboto. So, what we want to do as our part in this network is to obtain a novel bond substitute that can tailor the behavior of the 3D implant, and so to control the right place and the right functionality at the right time after the implantation. To do that, we have to know where we are working. So we have to speak a little bit about the bones. The bone is composed for, the 65% of the dry weight of the bone is the bone mineral. Generally is considered to be the stoichiometric hydroxyapatite, but as we know, and as it was well explained by Leroux in 1987, the real bone mineral is a bit more complex, and it is a highly substituted structure. This structure is also non-stoichiometric, it is nanocrystalline, and it has a high surface reactivity because of the hydrated layer that it is present around these nanocrystals. And furthermore, when we increase the scale, the structure is highly porous and then therefore is vascularized. This is resorbable because of its high reactivity and the nanocrystalline shape of the crystals. And of course, then, because of everything that I just said, it participates in the bone remodeling. So in our case, we decided to focus on the particular non-carbonated substoichiometric nanocrystalline apatite. It is a synthesis method that it is extremely used in our lab here at the CIANFLONE, and it's a structure that is easy to dope and to substitute with bioactive ions in many sites, or to functionalize it with biomolecules, enzymes, or antimicrobial agents. In our case, we will focus on the substitution with 3 metal ions that are silver, copper, and zinc, that are all reported in literature as being to be antimicrobial. And therefore, there is the copper and the zinc that are also reported to be osteogenic, and the copper is showing some interesting androgenic properties. These particles are then the base to the core of our work. That is the realization that we look for of a core shell microparticles dually substituted. What is the purpose of this particle? It is to have within the microparticle the control of the behavior after implantation and after in the following phases of the following life phases of the material. Why that? Because by tailoring the structure of the particle, we look for the possibility, for example, to have first a strong antimicrobial action, and then at the liberation of other ions that can enhance or help the growth of the bone. And then finally, we want to use these microparticles to produce a 3D composite scaffold using the freeze-casting technique. That is a technique that works at low temperature and that has a wide range of polymers that can be used, and of course of biopolymers. So let's focus on the synthesis of the different nanoglycerin apatite. The synthesis method, as I just said, is widely used at the CIRIMAT of Toulouse. And in my case, we just focus on two modifications of the normal synthesis protocol. The substitution at the level of the calcium side, adding the metal ion just mentioned, and the variation of the counter ion of the phosphate salt that we see here. The synthesis can be modulated on many maturation days, but all the samples that I will show today will be of 1 day of maturation. As you can see in this short video, the synthesis is just a co-precipitation in which we pour the calcium or calcium plus ion solution in the phosphate solution. We work in a large excess of phosphate salt in order to have an auto buffering of the media, and then working at the buffer pH of 7.2 that is close to the physiological condition. And what we obtain is these two structures that, as we can see, of course, they recall the stoichiometric hydroxyapatite that, of course, here, other than stoichiometric, it's also sintered, so it's very well defined. Most of all, it is very similar to the natural bone. That is the kind of structure that we look for and that we want to attain. Clearly, because of the low crystallinity, the spectra are not well defined. So to complete the characterization, we do also an FTIR analysis, and we can observe that the spectra have a good accordance between referring both to the stoichiometric hydroxyapatite and the bone mineral, of course, with the exception of the zone where the traces of the collagen and of the organic matrix of the bone are left. We can make a small zoom on two zones to furthermore demonstrate the non-stoichiometry of the crystals. And in fact, we can observe the decrease of the apatitic OH band and the appearing of the non-apatitic HPO4 bands. This synthesis is the basis of the synthesis of the three monosubstituted apatite that we show here. We observe that as I said before, we work on the substitution with copper, zinc, and silver. And the first thing that comes up to our side is that at all the tested substitution for all the samples, we don't observe in the XRD patterns any secondary structure. So we have attained our first objective, that is to have monophasic materials. Then we can also look forward to the molar substitution ratio. We noticed that in the copper and zinc apatite, we have a good accordance between the theoretical substitution ratio and the experimental molar substituting ratio that was measured with the atomic absorption technique. This accordance is less present for the silver apatite that has to be synthesized in particular condition because of the sensibility of the silver itself. And we observe gradual differentiation from the theoretical ratios in the case of the silver. Furthermore, one last thing, we can observe that in the case of the copper apatite and in the zinc apatite, we use sodium as a counterion because adding sodium as a counterion of the phosphate salt granted us the possibility to increase the substituting ratio without having any secondary structure. That wasn't possible in the case of the silver apatite that was synthesized with ammonium as a counterion, and that showed also a better crystallinity of the crystals at all the substituting ratio. And so therefore, yeah, we obtained at first the bone-like structure that was the first our first objective, and we didn't have any secondary structures in these studied conditions. Now, we know that these ions are widely studied for their antimicrobial and their biological properties. In our case, today we will show, for a reason of time, just the more extreme case, we can say. That is the stereotoxicity of the pellets of silver apatite. This condition was studied essentially for one reason, because silver is the ion that is more likely to show anti-cytotoxicity in vivo, and the pellets are the condition in which we have the higher concentration of silver ions. As we can observe by this analysis, both on the SCM images and on the histograms, we have a good viability of the MG63 osteoblastic cells even on the pellets, and we can also observe that we have a relative increase that is higher between day 4 and day 7 for the silver apatite and for the apatite than the normal apatite. And we can also observe the morphology of the cells that is healthy, and that is the kind of results that we expected for healthy cells. We also made some preliminary antimicrobial tests against Escherichia coli and Staphylococcus aureus, and we observed both by the CFU counting and by the SCM images that we have the bacterial lines that are basically inactivated. We say that why? Because even though the bacteria were present, their morphology was not coherent with the possibility of them to just doing mitosis and to develop on the surface of the pellets. Then we can go further and study the realization of the core shell particles. To do that, we started to look for the spray drying technique. The spray drying technique is as simple as the name says. We have the spraying of a solution and the drying at the level of the nozzle, here and here in the real machine. Then the particles that are exposed to a high temperature for a fraction of seconds go through the drying chamber and then gets aspirated and then separated in the cyclone, where we can collect the powder at the end. The whole process is very fast and can grant a control of the morphology of the particles and on the size of the particles. And it is also suitable for thermosensitive reagents because the exposition of on the higher temperature is essentially esteemed in a very short fraction of seconds. This technique is extremely old. It was first patented more than 150 years ago. And since 1975, it was the subject of almost 28,000 papers. These papers can touch all the fields that you can imagine, even the entomology. It has 300 papers published related to the spray drying technique. There is just one thing that is almost missing, that are the biomaterials. There are just a small fraction of papers that involves the spray drying and the biomaterials. Furthermore, we want to control the structure, as we said before. So for that reason, we wanted to use the 3-fluid nozzle spray drying. It has a setup that is similar and equal to the one that I just shown, but with a nozzle that is concentric and that can grant us to use 2 different feedstock and to obtain a biphasic drop that then can hopefully be dried in a correct structure. Right now, even though it starts to be some years that the three-film nozzle has been developed, there are not many papers working on it, and most of them look for the encapsulation of drugs in polymetric shells or whatever. In our case, we decided to work with this technique and to try to adapt it to our systems, because it is a technique that, other than the good properties that we just showed, it can really grant us the possibility to control the structure in the 3 dimensions of the particles. And to do that, we worked toward the obtaining of physical gels based on our apatite synthesis. We just emulated the same synthesis that we did, that we showed before, but after the phase of filtration and washing, we rediluted phases in order to obtain these tiny physical gels. Sorry. So, we then tried to obtain at first a crucial structure having zinc as the core of the particle and copper as the shell of the particle. And we tried 2 different combinations of the concentration in solid particles of the gels. One with the 2 particles, with the 2 gels that are at the same concentration, and another one with the core that is at a higher concentration. We can observe at first that the XRT patterns are coherent with the dried powder and, of course, with the natural bone. And differently from the usual apatite crystals, we can observe that the morphology is quite controlled. And even looking closer to the steroids, we can observe this surface rugosity that could suggest us that we had really an agglomeration of the nanocrystals that we have, of the apatite nanocrystals that we have in solution. At this point, it started one of the most challenging parts of this thesis work, to properly characterize them. Finally, after some trying at the Centre de Microcharactérisation de Raymond Cassin, we tried to adapt a method that is the fib milling and the XRD analysis and the EDX, analysis. We tried to adapt this method that is often used with other materials to our materials. It wasn't very easy because often the apatites are not very comfortable in the FPM conditions and with the film milling, but we managed to cut them in half and to try to characterize the inner core, the inner phase of that. So at first, we observed by the EDX analysis of the section of the particle that had the 2 gel at the same concentration, that we hadn't a real separation of the inner structure in the EDX. We see copper almost everywhere and a tiny increase of zinc, but that it's not that good. On the other hand, when we had the core that was at a higher concentration, we observed a very nice isolation of zinc in the inner part of the particle, with the shell that is enriched with copper, and unfortunately with not much more information, because the technique it is nice, but it has 2 limits. The first one is the penetration of the EDX beam, because we have to analyze just the bigger particles, because otherwise we risk to have a bulk analysis that's not what we want. And then we lose the sensibility of the technique closer to the sample holder. So we can say the second third of the EDX analysis often is not that reliable. But at that point, we can understand that we can obtain this kind of partial structure, but we have to avoid the mixing of 2 phases that are essentially the same phase, because it changes just an ion in the structure, but for the rest, they are the same. To try to optimize this process, we did some viscosity measurement on the gel that we prepared with a rotating viscometer, sorry. And we noticed that for all the gels, we noticed a non-Newtonian behavior, that is a shear seaming, that already suggests us that the nanocrystals present in the gel have interactions one within the other, because otherwise we couldn't see this kind of behavior. And we also noticed that the copper and the zinc physical gels at the same concentration had more or less the same order of values of viscosity. On the other hand, for the silver case, the values were almost the half that we compared to the one that we see for the others. That can be due to the counter ion and to the higher crystallinity, because the higher is the crystallinity, the lower is the surface reaction. So that could be one of the explanations. In any case, based on these geological results, we started and we tried to optimize our method by doing several particles with different concentration ratio between within the core and the shell. And especially, we tried to link the concentration ratio, that is a parameter that is intrinsic of the apatite gel, that can so then change from ion, from counter ion, from almost everything, to the viscosity, that is an independent parameter that can be optimized and can be easily measured and can be also, of course, extended to systems that are not apatite gels. So at first we synthesized these particles, and you can see a good coherence of the diffractograms with the usual structure that we have seen along this discussion. And also the morphology and the rugosity are the same that we already have seen. And we can observe at first, after feed milling, the EDX analysis of these particles. As you can see, by decreasing the concentration and the viscosity ratios from 1 and 1.5 to lower than 1, we don't have, and we never have a proper core shell structure. On the other hand, by increasing this concentration and by increasing the viscosity ratio up to 4.22, we have a segregation of the copper in the outside and on the zinc in the inside. So, as a conclusion of this, we can obtain different core shell structure. We can optimize this kind of core shell structure by assessing for our condition and for our system that is a necessary a ratio between the inner and the outer viscosity of at least 2.5 to get these proper structures. Now, we wanted to vary the ion, because maybe zinc copper could have been just a lucky shot. So we tried to do two other combinations that are both with the copper as the core and with the zinc as a shell in one case and the silver in the shell in the other case. And as we can observe, we have for both cases the zinc that here is in the shell that is outside, and the copper that is segregated inside, and the silver that is in the shell outside, and the copper that is segregated and well separated. In conclusion, we were able to optimize the triple nozzle spray drying technique. We obtained this kind of core shell particles, and we managed to link the concentration to the viscosity in order to even try to expand the borders of the technique. Now, what we want to do with them, we want to see their evolution patterns, we want to study their cytocompatibility, and we want to use them. At first, we did the distribution, we studied the distribution patterns. Before studying the core shell systems, we studied the monosubstituted spray-dried system. So we studied 3 particles, copper, zinc, and silver spray-dried to have, as you can see, the same morphology and the same size distribution. And we studied the distribution in potassium hydrogen phthalate at 3 different pH. 7.2 that is close to physiological, 5.2 that is close to the pH that we have and we experience in the inflamed site in the body, and 4.2 that is an extreme condition that is also good for us to study to fasten the distribution of the particles. At first, we can observe by the distribution patterns of the monosubstituted particles, and it pops out to our eyes that the substituting ion has an effect on the thermodynamic of the particles, of course, and related even on the solubility. And we can observe that in the time range that we studied in these experiments, only the copper was almost dissolved as the one that was almost completely dissolved. The zinc and the silver apatite were clearly more stable than it. When we started to study the core shell zinc copper particles, we observed, of course, the same patterns. But this kind of dissolution patterns were, I mean, we wanted to deepen the study on them. So we calculated the release rate that we had in these systems. And we compared the release rate of the core of the shell of our core shell particles and of the core of our core shell particles with the monosubstituted particles that are comparable. So we observed that the shell of the zinc copper particle had a release rate extremely comparable with the with the monosubstituted copper apatite particle. But on the other hand, we observed that the core of the ring of our core shell apatite had a release rate almost 3 times lower of the monosubstituted particle. This can be due to the segregation of the zinc, of course, within our shell, and also the fact that we don't observe this release starting in a second time. It can be linked to the fact that in this condition, after 10 minutes, we have almost already 10% of the copper that is released. So of course, we expose the zinc in the very first minutes of the process. But nonetheless, we see that the zinc in the core is that segregated that it has a release rate that's 3 times lower than its equivalent monosubstituted particle. Then we prepared 4 other particles that are like 3 different substituting ratio of zinc per shell particles and 1 copper silver core shell particle. And we studied during my segment in the University of Porto, we studied the cytocompatibility. Against the MG63 osteoblastic cell, we can observe a general that generally at all the condition and in all the case, the concentration and the time points, we were above the limit of the 70% of the control that assess the cytocompatibility of a material. And we did the same analysis again toward the bone marrow mesenchymal stem cells, and you observed the same behavior with the exception of the higher concentration of the copper silver apatite. So we can assess that this particle at almost all the conditions were cytocompatible, and that they can show an effect on the cells that is time dependent and dose dependent. And nonetheless, what is very, very nice for our characterization purposes, it doesn't seem that in this case the substituting ratio has an impact on the cell viability and cell proliferation. Now, we want to use them in a real three-dimensional material. So we decide to use the freeze casting technique and to realize a composite scaffold between the mineral phase, that are the particles that we just discussed, and the sodium alginate, that is a polymer that is widely discussed and widely used for biomedical applications. And furthermore, it is soluble in water. And being soluble in water, we can control better, and we have a wide knowledge over the phase diagram of this solvent. That is fundamental because, as you can see in the video, we prepare the alginate solution. We mix and homogenize with the particles. Then we pour it in our mold and we place it in our prototype to freeze it from the bottom to the top, and to obtain a well-freezed structure that then is freeze-dried and show an interesting oriented porosity because of the vertical crystal growth that happened in the technique. So in our case, we use 4.6 milliliter of solution to obtain our scaffolds that are the one that you can see the condition. And since these scaffolds are meant to be used for bone substitution, they have their inner structure have to be widely characterized and have to be a good orientation, because otherwise we don't have any possibility of the growth of blood vessels. A good pore dimension, because otherwise the cells will not colonize the scaffold, and then we want even to know the particle distribution that we added to understand what happened to them. To at first, using correlation J, that is a plugin of the image software, sorry, we can observe that following the freezing front and looking at the scheme that described the orientation compared to the central axis, after a first very tiny disorganized phase of the germination of the solvent and of the orientation that goes more or less plus or minus 45 degrees from the center, we see that once we reach the steady state, the orientation of the pores is perfectly vertical and is organized as we want. This kind of orientation has been also corroborated by micro-CT analysis performed with the Fédération Fermat, in which, by doing a regional interest characterization, we also were able to estimate the total porosity of the scaffold that was of the 52%. Then we wanted to study the size form, and to study that, we worked on the top view of the scaffold. And in this case, we were able to observe that most of our particles had a peridiameter of more than the 150 microns, that is the diameter size that usually is defined to be the size suitable for the cell colonization. Finally, we studied with the SCM the same slice of scaffold to study and to observe where the particles were. And we observed that in all the zone and all the magnification, the particles are well and homogeneously distributed. And furthermore, they are embedded in the polymer walls, and their morphology is kept. So the process doesn't bother the structure of the particles. Even that was studied with the micro-CT and doing the regional interest preparation, and we observed the corroboration of the well-distributed, the good distribution of the particles. Here at the CIANFLONE, we also made some preliminary mechanical tests on the dry scaffold that we just prepared. And we can observe that comparing the alginate scaffolds that are in black, both on the transversal compression, in the axial compression of a small square that we cutted from our scaffolds, we have a good increase of the mechanical properties on both directions by adding the core shell particles, because they will impede a bit the sliding of the walls. But then we wanted to improve these properties, and we want to improve the stability of the alginate. That is known to be not the more stable polymer in solution. And we decided to perform a chemical cross-link by immersion of the scaffolds in a solution of calcium chloride or calcium plus magnesium chloride. After doing that, we did the same mechanical analysis in a state that was technically dry, but very humid, because we had a water-to-polymer ratio of almost more than 19. And we observed even a not very expected thing, because we observed that this starting zone of the curve that wasn't the one that we expected. Comparing that to literature, we noticed that this kind of slope was more compared to the one of the cross-linked hydrogel of alginate than to the one of our scaffolds. And we can also observe that after the first phases of the compression and after pouring out the water from the scaffolds, there is a changing of the slope and we observed the mechanical behavior that we expected. This kind of behavior was also being corroborated, was even more enhanced by the transversal compression. But in the case of this transversal compression, having a cube with all the pores open, the most interesting aspect is that, as you can see in the video, we pour out all the liquid. And even though we have a damaged structure, we reabsorb almost everything. Now, this kind of scaffolds were, of course, analyzed and studied to observe their cytocompatibility. We studied again during another segment that I had in the University of Porto toward the MG63 and the bone marrow mesenchymal stem cells. And we observed that even though it was present a preliminary inhibition effect of the particles within the scaffold, that the viability and the proliferation of the cell was still present after 21 days, and the same behavior was observed for the bone marrow stem cells. Finally, all the scaffolds were studied against the Staphylococcus aureus to observe their antibacterial activity, and we can observe that all the 4 samples that we prepared were showed antibacterial properties, especially compared to the alginate alone without particles. Exactly what I was saying. So, in conclusion, we started from our nanocrystalline apatite, and we managed to synthesize several biomimetic nanocrystalline apatite. We tested several synthesis parameters, and we tested several ion substitutions, and also making some biological tests on the powders and on the pellet. We also managed to prepare several physical gels and to study their behavior in view of the spray drying process. And we also, with the spray drying, managed to realize many particles with a spatial control of the substituting agent. We obtained several ion combinations, and we defined several parameters to try to optimize the method at best. We also studied the dissolution patterns and the cytocompatibility of these particles. And then we obtained some alginate apatite composite scaffolds. We tailored the oriented porosity. We evaluated the inner structure and performed a chemical crosslink of the scaffolds to improve the mechanical properties and the stability in aqueous media, and also demonstrated that they are cytocompatible and antibacterial against the Staphylococcus aureus. A good synthesis of all that we have done is the sample alginate apatite zinc copper 2.5%, because it is on light, it is core shell, it has a porous structure, and it is, of course, cytocompatible and antimicrobial. In perspective, we can work and we can deepen the study on the apatite gel, and we can optimize the realization and characterization of these gels even to scale up our system. We can increase the variety of ion combinations, so we can improve the characterization of the interface, of course, and we can try to extend this technique with the parameters that we studied to systems that are different from the apatites. And then we can really enjoy our time with the freeze casting, and we can vary the alginate apatite ratio, we can vary the alginate concentration, we can vary the polymer that we can use, and we can try to realize complex structure within our scaffold. Furthermore, we can also try to functionalize the materials with bioactive molecules. In our case, during the internship of Margherita Cescon from the University of Bologna, we started to use the trypsin, that is an antimicrobial enzyme, and we started the functionalization of the nanocrystalline apatite on the spray drying apatite and on the scaffold, obtaining some interesting preliminary results that I am willing to discuss with you later if you want. And in conclusion, I want to thank everyone here at CIRIMA for this 3 years of hard work, but very nice work. And of course, all the people that collaborated with me in Castaing and in Forkheim, and especially in Port. And I leave you the word to the president. Thank you.
Thank you. So thank you, Edoardo, for a very nice very pedagogic presentation. I think you have well put highlight the best and the diversity of the results that during your thesis. And the video also were very nice for